Hello everyone, welcome back. So today we are going to start with the behavior of RLC with respect to AC signals. So to start with, first let us consider pure resistive circuit. So in pure resistive circuit, so let us consider a pure resistor R here, which is connected across an alternating source V as shown in the figure, and the current flowing through the circuit is given by I. So the voltage we can write it as V equals to Vm sine of omega t, right? So now to determine the alternating current, so I, as we know, is given by V by R. So now here V is Vm sine of omega t divided by R. So now this Vm by R can be written as Im sine omega t. Here Im is given as Vm divided by R, right? So now if we consider, and let me again write it here, so it is Im sine of omega t. Now if you recall whatever we have discussed in our last classes, so about AC signals and the phasor diagrams, so we have discussed, so phasor is a representation of an alternating quantity, an AC signal, and here if we consider V to be represented like this, so if this is the signal of voltage and this is suppose minus Vm, and this is giving the voltage with respect to angle theta. So now here the current will be, waveform of current will be, okay, let me use another color, visible color. So the current will be in the same phase but with somewhat less than the value of maximum voltage Vm. So now this is Im and this is minus Im. So this is the waveform. Now if you move into the phasor diagram, then if this is given as voltage V, then the current will be given by, it will be moving in the same line, right? So this is current and this is the voltage, right? So I hope I am able to make you understand. So this is the phasor diagram. Now moving further, if you want to determine the impedance, then impedance is given by Z equals to V divided by I. Now here it is Vm Im sin omega t, which is Vm, and the Im we can also write it as Vm by R. So Vm gets cancelled, so remaining is R. So the value of the impedance is R. So now phase difference, as we know both are in same phase, so the phase difference here will be equals to 0. Okay. So now next thing what we are going to determine is the power factor. Okay, let me get some space here. So next is power factor. So power factor is given by cos of phi, that is the cos of the phase difference. So cos of 0 degree is given as 1. So this is the power factor of RC circuit. Now moving on to the power. So power is given by P equals to V into I. Now V is Vm sin omega t and current is Im sin omega t. So we have Vm Im sin square omega t. Now this sin square term can be also written as 1 minus cos of 2 omega t divided by 2, right? So now if we break this term, so Vm Im divided by 2 is one term, and second term is Vm Im divided by 2 multiplied by cos of 2 omega t, right? Now here this part represents a constant term, that means this value will always be constant, right? But on the other hand, this part contains a cos 2 omega t term, so it is a fluctuating part. So it is a fluctuating part. That means in the positive half cycle, whatever be the value we get here, in the negative half cycle, the value will be opposite. So that means the power that will remain working will be P equals to Vm by Im divided by 2, because this term will be 0. So this is also known as the average power. Now this we can also write like this: Vm divided by root 2, then Im divided by root 2. So the power is the RMS value of voltage and current. So what we have discussed here is, what we have discussed just now is the behavior of pure resistive circuit. So in case of pure resistive circuit, what we have seen is the voltage and the current remains in phase. That means there is no phase difference between them whenever we are applying only resistance. Now here Vm is sin omega t, current is becoming as Im sin omega t, and the impedance would be resistance only, since we would not have any other components. Then since they are both in phase, voltage and current, so that is why the phase difference is 0. So power factor becomes cos of 0 degree 1. Then power contains two terms. First one is the constant term, and second one is the fluctuating term. So if we determine the average power, then the fluctuating term will become 0. So finally the power will be Vm Im by 2. So that we can also write it as divided by root 2 on both terms. So both we can consider that the average power is given by the multiplication of RMS values of voltage and current. So this is for resistive circuit, purely resistive circuit. It doesn't contain any other component of capacitor or inductor. So now next let us consider what will happen if we have a pure inductive circuit. So let me draw a line so that we can write it side by side and compare. Okay, let's proceed further. So next is behavior of pure inductive circuit. So next is behavior of pure inductive circuit. So this is the circuit diagram. We have a AC source P, and we have an inductor L, and the voltage across this is VL, and having a current of I. Now let us consider this circuit. So it is a pure inductor circuit connected across the alternating voltage V, as shown here in the figure. So now here let us consider V equals to Vm sin omega t, like always. So if we determine the current, then the calculation of current is given by V equals to L vi dt. Now from here, if we determine the value of I, which will be 1 by L integration of v dt. So now this integration will be for Vm sine of omega t dt. Now this will be, this Vm is a constant term, so it will come out Vm by L. Then we have minus of cos omega t as the integration, and then divided by omega. Now this will be Vm divided by omega L. This minus cos omega t can also be written as sine of omega t minus pi by 2, right? So now here this term can be replaced by Im, and it will become Im sine omega t minus pi by 2. So this is the current I. Now where Im is given as Vm divided by omega L. Okay. So now considering this, if we draw the waveform, then so suppose this is our voltage V, Vm, then minus Vm, this is pi, this is pi, this is 2 pi. Now the current is given by Im sine of omega t minus pi by 2. That means the current graph will start after pi by 2. That means this is pi by 2. So the current waveform will start after pi by 2, right? So that means there will be a phase difference now. So now if we draw the phasor diagram, then if this is voltage V, then current will be lagging by 90 degree, so it will come down here, and this angle is 90 degrees. So this is our phasor diagram now. So now after phasor diagram, what we require is next is let me see what we have written here. After phasor diagram, we have to determine the impedance, then phase difference. Okay, so let's see the impedance. So what is the impedance? So impedance is Z equals to V by I. So now here we have this term as Vm divided by Vm by omega L, so which will be omega L. So Z is given as omega L. Now here omega is also known as, also can be given as 2 pi f, right? So this is called as impedance. So this is the value of the impedance, which contains the reactant part. That means it contains a term which contains the inductor, right? So this is the value of impedance. Now this omega L is also known as XL. We also represent it by XL, which is the inductive reactance. Now if we consider for DC, what would be the value of this XL? So for DC, the frequency is given by 0. So the value of XL will be 2 pi FL will be equals to 0. So for DC, the inductor behaves as a short circuit, right? But in case of AC, it is not a short circuit, but it will provide or it will offer some reactance. Okay. So now moving on, next is our phase difference. So phase difference is pi is 90 degree. So the power factor is next. So power factor is cos of pi, so which is 0. So power factor becomes 0. Now coming to the power, so let's see what is the value of the power. Power is given by V into I. So if you write it Vm, this is sine of omega t into Im. Let me write with respect to cos term only. Cos omega t, we had a minus sign here. So this term can also be written as Vm Im of sine of 2 times of omega t divided by 2. This is minus, right? Since sine omega t cos omega t is sine of 2 omega t by 2. The average power, if we determine, so the average power in this case will be 0 because this term is a fluctuating term. So this will be the power for inductor circuit. So in inductor circuit, the power consumed by pure inductive circuit is 0. So this is for inductive circuit. So now let us move for capacitive circuit. Okay, so moving on, so we have next is pure capacitive circuit. So here we have, let us consider a pure capacitive circuit connected across the alternating voltage V and which is carrying a current I. So now as we have written earlier also, so V equals to Vm sine of omega t. Now the current in a capacitive circuit is given by C dV dt. So now if we expand this, this will be ddt of V is Vm sine of omega t. So now V is a constant term, so it will come out. So Vm to C, and we have sine omega t will be cos of omega t multiplied by omega. So this is omega c into Vm into cos of omega t, which will be, we can also write it as Vm divided by 1 by omega c. This cos omega t can be written as sine of omega t plus pi by 2, right? So this is the relation of current and voltage. So current is I equals to Im sine omega t plus pi by 2, where Im equals to Vm divided by 1 by omega c, right? So this is the Im is the maximum value. So now moving on to the waveform. So I have already drawn it here. So if this is the waveform for voltage, then the current waveform will be starting before voltage waveform by pi by 2. So that means it will be starting beforehand and the waveform will be like this, right? So now moving on to the phasor diagram. So since current is starting before, so that means current is leading voltage by, sorry about that, current is leading voltage by 90 degree. So now current comes here and this angle is now leading by 90 degree. Now let's move into the other part, that is the phase difference. So phase difference is 90 degree. Now power factor will be cos of 90 degree will be 0. So now moving on to the power. So we have V equals to Vm sine of omega t, and this is Im Okay, instead of sine we can directly write cos of omega t. So this is also again similar to the inductor circuit. So if I put 2, this will become sine of 2 omega t, since sine of 2 omega t equals to sine omega t cos omega t, right? So this equals to a term which is fluctuating in nature, so that means average power will be 0. So that means the power consumed by an capacitive circuit is also 0. So these are the relations of RLC, pure RLC with respect to AC circuit. Okay. Yes, one term is left, that is the impedance in case of capacitive circuit we have to determine. So let's see what it will be. So it is given by Vm by Im, so it will be Vm divided by Vm divided by 1 by omega c. So this is 1 by omega c, which is known as capacitive reactance Xc. So now for DC, what will happen? In DC we have frequency equals to 0. So Xc equals to 1 by omega c is given by 2 pi Fc. So here frequency is 0, so this term becomes infinite. So that means in case of DC circuit, the capacitor behaves as a open circuit, or it provides a maximum amount of resistance or impedance, right? So in case of DC, the capacitor doesn't work, and in case of AC, it will have a capacitance value, right? So these are the derivation with respect to R, L and C. Okay, so I hope you have understood. So next we'll see what is the relation of RL circuit and RC circuit, and later we'll see what would be the relation with RLC circuit. So stay tuned.